Hi everyone and welcome to a new video about electric circuits. This is our second example about the mesh current method. In the previous example number 1 about the mesh current method, we have discussed a relatively simple circuit. This is a more complicated circuit to illustrate the concept also in great detail, and we will discuss the Wheatstone bridge where we can determine the current to a load. So this is our second example. Of course, we'll work out the calculations for this example step by step and also verify these in our SPICE simulations. So let's look at our example and also the values we need. Now we have the circuit here. As said, is a Wheatstone bridge. It's actually used for let's say the string gauges, all other elements to have a specific voltage across the points A and B. The voltage here is a DC voltage, so that is 100 volts. R1, R2, R3 and R4 are also given, and also the load is given. So we have 5 resistors here and 1 DC voltage source. Again, using mesh current method, we would like to calculate the load current. That's actually this current in this direction, so from left to right. And also the power delivered by the DC voltage source Vs. So 2 things we need to calculate. Okay, now let's see how we can do the solutions. Now step 1 is to choose the loop directions. Now we have now here a little bit complicated example compared to example number 1. We have actually 3 loops. If you look at it, you actually have a loop here. That's actually this loop or the other one. So you can choose one of these. There's also a loop here in between. So the first triangle, let's say, the upper triangle. And you have also a triangle here, which is also a loop. So we can actually set up the first loop, and I call this the loop current Ix. We have another one, Iy, another one, here is Iz. You can also call it Ia, Ib, or Ic, or whatever you want to call it, just to name them and to work it out later correctly. Now this is the orientation I have used. Again, clockwise, but you can also choose to do everything counterclockwise or any other mix. No problem at all. Just keep everything from the beginning to the end exactly the same. That's actually what it is, and you will get exact same answers without any minus sign problems. So the step 1 is choose the loop direction, and then we have the loop X. So we develop directly also the equations. So what you see is actually if I start here or there, doesn't matter, and then end at the same point where I started, I see actually minus Vs because I start here and then look up, and I see R1 and R2 in the direction, the same direction of Ix. So that's actually why it's called minus Vs plus in parentheses R1 plus R2 for Ix. But I see that Iy is actually in the opposite direction of Ix, so it's actually fighting back. But then specifically, of course, for R1. Now for R2, the Iz is actually in the opposite direction of Ix because Ix is going in this direction and Iz will go in that direction. That's also why we have a minus R2 here times Riz. Now everything here is 0. Now similarly, we look at loop Y. Again, our orientation is clockwise, so we will do first, let's write down all the, let's say, the resistors that are positive for Iy, which are R1, R3 and RL. R1, R3 and RL. So that's actually for the Iy. That's why we have plus sign here. I already placed it actually in the order from X, Y, Z. Now you also see again the Y is going in that direction, but Ix is actually going in the opposite direction, so it will again fight back. So, but then specifically for R1, and again we have a minus R1 times Ix. You also see for the load actually part, or load resistance, we have Iy in this direction from right to left, but the Iz is going from left to right. Again, it's fighting back, and it is then specifically only for resistor RL for the load. That's actually what you see here. So minus RL times Iz. Again, everything equal to 0. Now, finally, similarly for the loop where we have the Iz as the current, everything for, let's say, the Z is R2, R4, and RL. That's actually shown here, R2, R4, and RL, everything for IZ, everything of course plus. But what is now fighting back, you can also see R2 is actually for specifically then IX is in this direction, but IZ is in that direction, so that is fighting back. So it's for the minus R2 times RX, IX I mean. And it's all for the load, because you have the IY is fighting back, so it's actually minus RL times IY. And add them up, and you get same 0. Okay, now we have this, and let's then write down the loop equations for each loop using the values. For loop X, just substitute what we have given, so 100 volts, etc. So this is the equation we have developed, and these are the values. So R1 plus R2 will be 700, so 100 plus 600. R1 again 100, and also R2 600. So that's what we have. Now we keep the unknowns, the variables left, and place the constants, the numbers, on the right side. This is what we get. We can of course simplify this. You can divide by 100 and you will get this much easy expression. Now let's call this equation number 1. Let's also do that for loop Y. Bring this equation again and then substitute the values that are given. We have minus R1, so it is minus 100. R1 plus R3 plus RL will be 550, because this is 100, 400, and then 50, so it will be 550. And for RL just, it will be then 50, of course with the minus sign here for this direction. Now we have this equation. Of course we can also divide this by 100 or just by 10, which one you prefer, but I just again do it divide by 100, and I get this equation, and I call this equation number 2. Now looking to the final one, which is loop Z, again get the equation back and also substitute the values. Again R2, R4 and RL together will be then 1450, so that is then 600 plus 800 plus 50, and the rest are just from the given. Again divide by 100, you will get this simplified form, and I call this now equation number 3. So I have 3 equations and also 3 unknowns, so I can solve this and I get a unique solution for the IX, IY and IZ. Okay, solve the unknowns. There are different methods to do this. You can again use substitution method, what we have used actually in the previous example for the mesh current method. But in this case we have 3 unknowns. Let's try and also work out a different method using the matrix method, matrix vector form. So we have now these 3 equations. So again, equation number 1, 2, and 3 on top of each other. And let's use matrix vector form, which is very useful and also handy to calculate, let's say, a circuit where you have more than 2 unknowns. Okay, now what is actually the matrix vector form? You actually only use the coefficients of the currents. You place it actually in a matrix. IX, IY, and IZ are your unknowns, and you place here, after the equality sign, the unknowns as a vector. So matrix, vector, and also the unknowns here. You need to, of course, have it in the same order. So X, Y, Z, X, Y, Z, X, Y, Z. That's actually also the reason why I have it in the beginning in that format. So 7 minus 1 minus 6, you can see it here, minus 1 plus 5.5 minus 0.5, it's all here in the second row. In the third row I get minus 6 minus 0.5 and plus 14.5. And this is just 1, 0, 0. That's all shown here. So I will now use this format to work out IX, IY, and IZ, which is much more compact than this one, and it will be also handy to work out later the unknowns or the unknown IL and also the power for the DC voltage source. So let's bring it here and also use this. Now we can convert this to a much nicer representation, which is given by this. So this is called also a matrix vector form, but it is much more compact. So you don't actually see these unknowns anymore, and you place this, let's say the solution or the answer for these three equations, as a vector next to this matrix equation. Now what we want is we would like to calculate the Ix, Iy, and Iz as said before. So for that we need to make this 0, this 0, and that 0. So that's actually the order to make that 0. So you start by making this 0, so minus 6, and I will show you shortly how you do that. That's also called the elimination method, or the Gaussian elimination in matrix or linear algebra courses. And also make this 0, the second one, and also make this 0. Now let's start with the equation and also work this out. So I will get this and start first with 6 times the row 2. The small letter r and then the subscript 2 means actually the row. So R1 will be then row 1, or R3 will row 3. So this here will be then multiplied by 6. Why? Because I have a 6 here, or minus 6 and a minus 6, so I can then add them up or subtract from each other, and then can calculate and make that 0. That's the purpose for, or the reason for making this 6 times the R2. Now I will get this. Of course, I don't change R1, also R3, so first write this down. The only thing that is changing is R2. That's actually only changed, so that will be then times 6, times 6, times 6, times 6. So every 4 elements here in the row must be multiplied by 6. Okay, then you will get this. Now you can see directly if I do R3 minus R2, that's the next step, you will change this. That's actually the reason or the meaning of this. R3 minus R2, that means you change R3 and the rest is actually the same. So we keep actually R1 and R2 the same. So let's write down R1 and R2 again, but R3 is changing because that's minus 6 minus minus 6 will be 0. Now minus 0.5 minus 33 will be then minus 33.5. 14.5 I mean, minus 3 will be then 17.5, and a 0 minus 0 will be of course still 0. Okay, that is exactly what I wanted. So the first 0 is appearing, and I have now actually done the first step. Now I want to have this 0. How can I do that? Of course I can say I will take the 6 over 7 times the row 1, but of course that will be a little bit difficult using fractions. The better way and also safer way is multiply this by 6, so row 1, and also multiply row 2 by 7. So what you get is the following. So you will change 2 rows. The third row will stay the same. This is then minus 42. Again, 7 times, so that will be then 231. 7 times will be minus 21. This also 7 times, of course, but this is just 0. I will multiply this by 6, 42, this by 6, minus 6, this by 6, and minus 36, and this also times 6, so it will be 1 times 6, will be 6. Okay, now next step is, of course, I did this because I want to have a 0 here, and I can now do R2 plus R1. So that's the reason for doing actually this step, in order to do this much easier. Now we have the R2 is changing and the rest is unchanged. So let's see, this is still unchanged. The R3, the row 1 and row 3 are unchanged, so you can just copy them from this part. Only this part is changing, so this will be 0. This will be 231 plus minus 6 will be then 225. Now minus 21 plus minus 36 will be then minus 57, and of course 0 plus 6 will be 6. Okay, what you see is we have now also get our second 0. The final one is this 0. Now you can do, for example, multiply this row 2 by 33.5 and also the row 3 by 225, or you can say let's use a little bit smaller number and first divide R2 by 3. then you get this. So only that will be 75 minus 19, and it will be 2. You don't have to do that, but that will be a little bit easier also. You don't have large numbers. Okay, now I have still an issue. I need to still get here a 0, this part. And I don't see or recognize at the moment, don't recognize any nice number to multiply, let's say, row 3 or row 2. So what I do, just straightforward, I will multiply this row 3 by 75 and this by 33.5. That's actually what I do. So row 3 by 75 and the other one with 33.5, so row 2. So what you get? Now row 1 is staying the same, nothing happening. So just copy row 1. First do that. Copy row 1. That's actually shown here. Okay, next one is, this will be then multiplied by 33.5. Also 75, then you will get this. And also minus 19 will be then multiplied by this number, 33.5. And also 2, that will be then 67. Now, for the third row, you will multiply this number, the 0, by 75. That will be 0. This one also, that will give you minus 2,512.5. The other one will be then 1,312.5, and the other one will be just 0. Now what you see here, of course, some large numbers, but the thing is, the nice thing is, now you have this number and that number, let's say alike, and they have only the sign different. So I can say, let's then add R3 to R2. So R3 plus R2 will means R3 is changing. That means R1 is stay the same, R2 is still the same. So I can copy them, and this will be 0. And this will be just this. So 1,312.5 plus this will give you this. And 0.67 will be, of course, 67. That's exactly what I wanted to have in the beginning, the triangle here as 0. Now I can see this 676 is actually times IZ, because that was actually, let's say, the formation of our matrix from our 3 equations we got using that mesh method. And that's equal to 67. So I can now calculate directly IZ. And then I can back substitute that in the second row and then calculate IY, and back substitute the IY and IZ in the first row, calculate IX. That's actually the next step. So now we can calculate these 3 currents, IX, IY, and IZ. Like I said, this third row will give me this equation, and I will now have 67 over 676 will be approximately 99.1 milliamps. I will just also make it blue to recognize this easily. The next one is the second row. That will be then 2,512.5 minus the 636.5 times IZ is 67. Now we know IZ, so I can now calculate IY. Now let's then rewrite this, place this to the right side, divide by this number, 2,512.5. Just substitute this in here, you will get 51.8 milliamps. Now, the final one is the first row. This sort of just work out actually what you see in the first row. So this 42 times IX, minus 6 times IY, minus 36 times IZ, that will be 6. Now we know the IY and also the IZ from the first 2 calculations. Now we can calculate IX. Just place these two to the right side, make it plus, divide by the 42 as the coefficient, and I will get 235 milliamps. Now I have everything I wanted for the first step. Okay, let's collect them. Let's make the summary. This is what we have for the IZ, IY, and IX. What we want for this exercise is the load current. The load current is going from left to right between point A and point B. If I look at it, it is actually in the same direction. The IL is in the same direction as IZ, but it is in the opposite direction of IY. So the actual load current will be then IZ minus IY. I know IZ and also know IY, so let's then just substitute this. So of course I can use exact values. So for IZ I can use 67 over 676. And for this I can also use this 35 over 676. Then I will get exact value 32 over 676, or approximately 47.3 milliamps. That's the load current. That's also for let's say question A. Now for the power delivered by the source, voltage source Vs, I need its voltage value and also the current it is delivering. That's actually this generic formula again. Power is equal to volts times the current, so the voltage times the current. Vs we know, it's 100, but I don't know yet Is, but we know that also because Is is here. And that is equal to Ix, and that is 235 milliamps. Just the same value we have already calculated. So we actually have it. Now we can say PS is then 100 times this, 0.235. That will give you 23.5 watts. Now we have it, and also in this form. Okay, now the simulation circuit is actually shown here, and you can see the voltage source, the resistors R1 and R3, R2 and R4. This is drawn in a different way, not in this, let's say, in a triangle on top of each other. It's actually shown in this configuration. It's the exact same meaning. Now what you see is also I have placed 3 current meters or current arrows, Ix, Iy and Iz, because Iz is going actually in this direction if you rotate like that. And you can now also see from the results what they are. Now you see here in the current for the, let's say, the load from 0.2 to 0.5, that is actually this node 2 to node 5, that's actually shown here. It is 47 point, let's say, 3 milliamps, and we have calculated that approximately. Of course, it is a little bit more accurate, and we have rounded off. Those are just rounding off errors, but this is just exactly what we wanted, and it's exactly also what we have calculated. Now, if I look at Ix, this one, it's actually shown here, it is 235.2 approximately milliamps. Now, very close to what we have, so that's also fine. Iy is 51.8 approximately, also what we have, and Iz is 99.1 milliamps, also what we have. So those are really confirming our calculations in this simulation. Now I will also show this now live in the simulation using Tina TI Spice. So let's jump to that, show the circuit I have prepared for you, and also show you how to generate this table, and also show you something more in that simulation. So let's jump to the simulator. Alright, now we are in the simulator. The circuit is already prepared. We have the voltage source, R1, R3, R2 and R4, and also the load are shown here. So these are the current arrows or current meters. That's actually from here. So this is the current arrow. And if I now do analysis, as we did in the first example, and do, let's say, table, or for, let's say, for difference, you can also say, let's calculate the nodal voltages. You can get directly the currents here because I have placed the meters. But if I again do the table, this I think much nicer, this table, let's bring it back here. And if I say, okay, I won't like to know the current here, just click on this component, you will get everything red. For this component, the current and also the voltage. We are interested in the current, you see 47.3 milliamps. Now, if I also want to have, let's say, this current, that's already shown here, but it's of course the voltage is 0 across this current meter, because that's the ideal situation. And you can also remove it and actually get the same result. So it's not actually needed here for this circuit, just to make this easy to see that the Ix, Iy and Iz is shown here. You can of course also look at the other elements, so make that or select that to highlight actually its current and its voltage value. So you don't need this current meters again, so I can remove it and then make this connection complete, remove it and make this connection complete, and remove it, make this connection complete, and run again. You will get exactly the same results. So bring it here, and then see here, you get again 47.3 approximately milliamps. I will continue in the next examples, video tutorials about node voltage, superposition, and also other theorems and methods to illustrate the concept for the electric circuits. So if you have any questions, comments, or any suggestions for these series, please let me know and I will try to answer them as soon as possible. See you next time in another interesting video. Take care.